My Physics 2 Lab 4 on circuits. So before we get started with our lab today, I'm just going to do a quick overview. So first we're going to have an introduction with the lab purpose and goals and then the fundamental principles used. Then we'll walk through the procedures of all the circuits we made in CCK. And then we'll go through experimental data, the results, and then we'll discuss all of our findings. So to introduce us to the lab, the overall goal here is to predict the behavior of circuits with resistors in series and in parallel, and to measure the actual values of conventional current and potential differences in circuit, as well as the behavior of ohmic resistors and capacitors. The purpose here is to use energy conservation and current conservation principles in building a circuit. For the purpose of our lab, our system will be all elements of the circuit, and our surroundings will be everything else. And as a general overview of our results, it is that our results will be equal to the initial current or energy due to the conservation of current and energy, which we'll see. So first, to get into our fundamental principles, we have Ohm's law, which states that the current flowing through a component is directly proportional to the voltage V across it and inversely proportional to its resistance R. This helps us to understand how energy is transferred to the circuit elements and how resistors affect the flow of electricity. We also have the node rule, which asserts that the sum of currents entering a node in a circuit must equal the sum of currents leaving the node. This ensures that energy is conserved at each connection point in the circuit. And then we also have Kirchhoff's loop rule, which states that the sum of voltage drops around any closed loop in a circle is equal to the sum of voltage sources was in that loop, so the change of the voltage is going to be equal to 0 in a closed loop. So this was our first circuit. This is showing energy conservation in a series circuit. You can see what our prediction was of what the current would be, and we can see that the actual current was pretty close to it at 0.2. So the measured current for both ammeters is 0.02 amps, and when we reverse the connection, the current reading on the ammeter stays the same. So when we added in the voltmeter, we replaced one ammeter with a voltmeter, which you can see down here. And when this happened, the current and the ammeter was 0, and our voltmeter was reading of 3 volts. So to find the path from the potential difference, which we can see here how we're going to measure this, the sum of the voltage surrounding must total to 0, and we'll show that on the next slide. So this was the path using the loop rule. We can see what the measured voltage was between each of these points, and we can tell that Kirchhoff's loop rule is satisfied, being that for the entire closed loop we have 0 volts. So for our observations here, when you attach the voltmeter to a circuit, it has a very high resistance, which means it draws very little current from the circuit. This minimal current doesn't affect the circuit's overall current, so the ammeter is designed to have very low resistance to measure current without significantly altering the circuit. Therefore, the ammeter reading remains ineffective. When you connect the voltmeter across the 100 resistor again, the ammeter reading was 0.02, and then when we replaced it in parallel, the current through the other ammeter is equal to 0.06, and this is because ammeters have 0 ohms, therefore the current doesn't travel through the 100 ohms resistor because there's no current at that point. So these are just the calculations that we were asked to calculate of the supposed values of resistance. And then we now have our RC circuit, so we can see our setup here. We have a 9-volt battery, a 200 mF capacitor, and a 30 ohms light bulb. We measure the voltage and discharge of the capacitor, and we plotted at 20 seconds of voltage which time, and we can see all of our calculations here with the graph to the right. And these are just some further calculations, and we can tell from our observations and calculations that our initial and final currents and energy are approximately the same, with just having a 2% error. So to just discuss, if we're doing this lab in real life and use an actual ammeter instead of an ideal simulated one, the real one has resistance, and the current is inversely proportional to resistance. So when resistance increases, the total current decreases. We also can think of the loading effect. So the presence of a real ammeter might load the circuit it's measuring, meaning it draws some current for its own operation. For our last question, basically the model predicts that it would charge immediately, but in real life this doesn't happen because the resistance is not actually 0. This can be done due to battery drain, erosion, and general wear and tear. Thank you.